All right, guys. In the previous video, we looked at GD&T in terms of its barest fundamentals of the tolerance zone, the basic dimensions, and the datums, and how they all sort of set up a framework around which we draw the different types of tolerance zones that apply to control that feature and the aspect of that feature that we're most interested in. And pretty much here in position, we're going to be dealing with cylindrical tolerance zones. When we get into things like concentricity and symmetry, that changes a little bit. But I always want you to remember that tolerance zones can be a lot of different things. They can be parallel lines, parallel planes, cylinders, concentric circles. In the case of profile, it can be any sort of odd shape that needs to be generated to follow the contour of the part. So at least at this point, we've already seen now that the GD&T gives us control of a tolerance zone that's highly variable. So I wanted to get that out. Now again, we're going to be hopping around a lot in profile or in position, just so we can get through the chapter. And again, a lot of the examples in this chapter, it just isn't worth going through because they're highly specialized. If you ever run into a scenario where you'll see them, you're going to have to go back to the book anyway. You're just not going to remember all the details about this. What I want to do here is, in this example, and this is right out of your handbook, figure 7.4, this is one of the areas of GD&T that I really don't like the way they've implemented a very critical distinction. You'll recall early on when we talked about form that there's a distinction, a very clear distinction between a surface element and a derived median element when we apply a feature control frame. Well, the same thing applies with when we apply a datum. The datum letters are sort of stuck on the surface or on a feature of size, and we've seen already that we can use the material condition modifiers to adjust the size of a feature, and we can or adjust the size of the tolerance zone based on the size of the feature, and we can also use that material condition modifier to adjust the tolerance zone based on the size of the datum features. Now again, this has a very practical purpose. The purpose is to allow us to design what we call functional gauging. Functional gauging allows us to sidestep a whole lot of inspection, and it's basically what it sounds like. It's a gauge that checks the function of the part. And as long as that function is met, whether it fits on the gauge, that's good enough. We don't do any measurement, we don't do any plus or minus this or that, we're just done with it. And it's a fast, easy, cheap, and very reliable way to guarantee that the part is meeting the requirements of the design. And in order for that to work, we do need the material condition modifiers. We need the material condition modifiers to apply both to the feature that we're inspecting and to the datums that are establishing where that tolerance zone is supposed to be. All right, but you saw even when we applied the feature control frame to the surface elements versus the derived median elements, it really takes a careful look at where the feature control frame was stuck, where it was applied, whether it was applied to the surface or if it was associated with or attached to what we call a feature of size, which is really the dimension that defines the dimension and the size. It's a super critical distinction, and it's a ridiculously subtle way to highlight one versus the other. So again, I've never liked it. I wish they would come up with a much better scheme. I know I could in about 15 minutes. But I want you to see this distinction, and I want you to make sure that it's clear, because it is going to affect how we interpret the datums and the feature with regard to the material condition modifiers. Okay, so here's a perfect example of it. We have a very simple part, what I call a block with a hole in it, in this case 5 holes in it. But we have two features. We have this larger hole and then we have 4 smaller holes. And the tolerance zones for these holes, this is a positional control. We are going to set up basic dimensions, locating the centers of all of these. And at each one of those basic locations, there'll be a defined tolerance zone that the cylinder, or that the derived median element or the center line of that hole has to fit within. And if you remember from last video, once that tolerance zone is there, the hole can tip, the hole can bend, or the center line can tip, the center line can bend, the center line can move fore and aft, back and forth, it can translate, as long as it fits within that cylinder. And never forget that the tolerance zone defined by this is not the feature itself. These could just as easily have been square holes. The tolerance zone and the feature control frame would not have changed. Okay, but what I want you to look at in this instance is the datums. Now, I made a distinction in the last video about whether a part was fully constrained or partially constrained, and that relates to what degrees of freedom it has to move in the coordinate system that's set up by the basic dimensions. The fully constrained means that 3 translational degrees of freedom, this way, and this way, are prevented from movement. And likewise, all the rotational degrees of freedom, the yaw, the pitch, and the roll, are all locked out. Here we have a good example of a very typical part where the datums are meant to fully constrain the part. We have a datum A, so I'm going to use this eraser again as an example. Datum A is the primary datum. It's a plane, and when that datum is applied, that means that this part must stay in contact with datum plane A so that we can never lift off those 3 points. So that prevents this translation. It prevents a roll. It prevents a pitch. Does not prevent a yaw. In order to take care of some more of those constraints, we have datum B. So if I put 3 contact points for A, 2 contact points for B, now I am no longer free to translate in this direction. I can still translate in this direction, but I can no longer roll or yaw. So I've locked out that rotational degree of freedom, and I still have one more translational degree of freedom that I have to lock out, and datum C does that. So 3 points, 2 points, 1 point. If I am obligated to touch all 6 of those points, this block cannot pitch, roll, yaw, or translate along any axis. It is fully constrained. So now we get into the scenario of what is the datum itself. What is the what element is actually the datum? Is it the surface element or is it the derived median element? In the case of A, it's obvious that datum A is stuck right onto that surface. It is not associated with the dimension of size, which I didn't even put up there. I think it is 14 millimeters and 12 millimeters are the limits of size. Okay, but this datum is not stuck here. If it were, it would mean something different than what you see here. And this is the distinction that I think is so hard for some people to catch. Certainly, a lot of experienced engineers don't even make this distinction. So The distinction here is, since this datum box is stuck to that surface or to an extension of the surface, in this case, it could just as easily have been stuck right to that surface. That means that the datum is the surface element of that surface. It is the actual physical surface, and it is the touch point, or the three touch points that make up that plane. Datum B and datum C, you'll notice they are actually stuck to where the dimension is. The dimension is 36 plus nothing minus a half. These again are all metric units. So this is inch and a quarter, inch and 3/8, something like that. And a half a millimeter is 20 thousandths. So it's a reasonable size part, and it's a reasonable tolerance. But in the case of datum B and datum C, as opposed to datum A, where the datum block is stuck is by the feature of size, or the definition of what the size of that part is. That now makes the distinction between A and these other two, where datum A was the surface. In the case of B and C, the datum is the derived median element. And in the case of this block, it is a median plane. So we have a plane, an imaginary plane, passing through through the hole in a vertical orientation. That is the derived median element for datum B. The horizontal plane passing through the hole is the derived median element for C. When we make that distinction, that means then that we are really obliged to evaluate the size of that datum feature and the size of that datum feature. In this instance, with datum A, we can't evaluate it because it is not associated with the size or the thickness of this block. Okay, so this, both of these features have the same limits. They have 36 millimeters and 35.5 millimeters as limits. We can now adjust the size of the tolerance zone for each one of these holes based on not only the size of the feature itself, the size of this hole, the size of this hole. We can use that size to adjust the size of the tolerance zone, locating the hole. As typical, we would allow these holes to move more if they were larger. And again, that makes perfect sense that everything will fit just as well if this shifts over 1,000th and that hole opens up 1,000th. That will have no effect on the fit of this part. Likewise this. Remember too that each one of these holes, each one of these 5 holes has to be evaluated for its size. And the tolerance zone has to be evaluated based on the actual size of that individual feature. So when you go to inspect this thing and measure to see whether those holes are where they're supposed to be, you first have to know what the size of each one of those holes is. And then you're given 1/4 millimeter tolerance. That's the minimum tolerance that you'll get. If this hole is at, this specific hole is at its least material condition, you'll get an increase in the tolerance accordingly. If it's at its maximum material condition, in other words, when the hole is at its smallest, that's all you get. Open up the hole 1,000th, you add 1,000th to that tolerance zone. It's, again, sort of an accounting game. You have to account for every 1,000th of size in order to evaluate the size of that tolerance zone. Okay, so that is the measurement of each one of these holes. Well, likewise, we have the material condition modifier applied to datums B and C. So when we're evaluating a specific block, we have to measure this width and this width. If it is at its maximum material condition, when the block is at its largest, we can apply no additional tolerance. We're stuck with this again. If we thin the block down a little bit, if we mill the edges down a little bit, we can get more positional tolerance for these holes. Now again, it's not immediately obvious. You almost have to do the mathematics of it to see that that really does work. But intuitively, you know that if these holes are bigger and these blocks are smaller, we can wiggle it around and get things to line up. And it works out mathematically just very well. In fact, there's a separate standard for the calculation of the tolerance zones, and it works out as well as you might imagine. But here's the thing, and I think it's always confusing to people first introduced to GD&T, is you've got 3 material condition modifiers, each one of them which has to be evaluated for that specific part that you have in your hand that you're inspecting, and each one of those can add to the tolerance zone. Now, it can never subtract from what you're initially given. You always get that. That is the least amount of positional tolerance that you're given. You can make it bigger by going away from maximum material condition. So when you read this, I want you to always think, when this hole is at maximum material condition, this is the tolerance I get. If this feature is at maximum material condition, that's what I get. Likewise, this feature, maximum material condition, is the smallest I get. So in order to get the least amount of tolerance, both the hole has to be at its smallest and the block has to be at its largest in this dimension and this dimension. So you've got 3 actors in here actually that can have an impact on how much positional tolerance you get. Sometimes this is called bonus tolerance. I don't really like that term, but it's kind of true, is that if you want to play with these dimensions, for instance, if this hole is a little bit out of position, you have the option of increasing the hole size or thinning down the block, and in each one of those cases, what was originally a part that was out of spec or a hole that was out of spec can be moved into acceptance, and that's a neat feature. But it does require that sort of at least arithmetic to determine what your tolerance zone is and whether you're in it or not. That'll sink in. I think the important thing I really want you to pay attention to is how this datum this datum block is attached. The critical distinction is it attached to the surface or to an extension of the surface, or is it associated with the dimension, either by being attached to the dimension line. That's the way it's usually done. This part, I think, is the part that I like the least, is that it really does force you to look at that. There's no other notation in the feature control frame or in the datum block. Now, I will say that you can sort of tell by looking at this feature control frame that datum A is not subject to material condition modification. That means one of 2 things. It means that, one, from the designing point of view, you can't do it. It just won't help anything. Or it's actually a surface element that we're using as a datum. All very confusing, and this is probably at the second level of sophistication of GD&T, but you do have to be able to make that distinction when you're evaluating this. And what you have to remember is if you do see a material condition modifier in a datum block, you have to go back to the size dimension that's associated with the datum and measure it and evaluate where are you. Are you at maximum material condition? If you are, tough. You don't get any additional tolerance. If you're away from maximum material condition and heading towards least material condition, then you have to determine how far, where are you within the limits of 36 and 35.5. And it takes a little bit of pencil work, or in the case of a CMM, it does it automatically, and you'll be able to evaluate this part properly.